Waves have energy. Whether it's sea waves, the light waves of a laser beam cutting through steel, waves in the Earth's crust causing earthquakes, or the waves which made the Tacoma Bridge shake itself apart in 1940. To take a closer look at how they behave, waves are best studied in a tank of water. The water appears to be moving from right to left. Pushing a dipper into the tank at one end produces a series of simple waves. The waves move along, but place a float in the water and it stays where it is. So what is moving, and in what direction? To look at waves in more detail, models have been devised to help explain their motion. Focus on just the orange spot and you'll see that it moves up and down. It oscillates. Although the waves travel from right to left, the particles on the surface of the water are simply bobbing up and down. This movement is at right angles to the direction in which the waves travel, so it's called a transverse wave. These waves are both transverse, but they look different. The difference is the distance from one peak to the next. It's called the wavelength and is measured in meters. The top wave has double the wavelength. Another characteristic of a wave is its frequency, the number of complete waves which pass a particular point every second. Change the frequency and see what happens to the wavelength. How are frequency and wavelength related? You can produce a simple transverse wave by moving a spring from side to side. Another type of wave is given a different name. This time a pulse is sent along the line of the spring. It's called a longitudinal wave. Fix a marker to one part of the spring and you can see that once again there's an oscillation. But this time the motion is backwards and forwards. For both types of wave, energy is transmitted along the spring, but the spring itself doesn't move forwards. Energy is transferred, but matter isn't.
This video will discuss the difference between transverse and longitudinal waves, how the speed of a wave is determined by the medium, and how to calculate the speed of a wave. Here's a transverse wave. Since it's a single disturbance, we can also call it a pulse. Propagation is the direction of energy travel in a wave. The medium is the material that the wave is traveling through. Here, the displacement of the medium is up and down. A transverse pulse is a wave in which the particles in the medium vibrate perpendicular to the propagation. If I produce a transverse wave, the propagation will be towards Mr. Peterson, but the displacement will be perpendicular to the propagation. Here we can see the transverse wave is propagating to the right, but the particle vibration is up and down, so that they are at right angles to one another. A popular physics question asks, if a wave is propagating to the left, what direction is point P moving? We know that since it's a transverse wave propagating to the left, that the particles can only be vibrating up and down. But how do we know whether it's up or whether it's down? Here's a way to visualize it so that you'll always get this question right. Look at the surfers that are waiting for the waves. When they're on the front of the wave, they're moving up. And when they're on the back of the wave, they're moving down. Since the wave is propagating to the left, the beach must be to the left. If the beach is to the left and the green dot represents a surfer, then the surfer must be on the back side of the wave. Which direction must they be moving? They must be moving down. Let's try this with the original question. The wave is again propagating to the left, so the beach is to the left. Point P, then, we can think of as a surfer, is on the front end of the wave. Which way must they be moving? They must be moving up. Longitudinal waves are different from transverse waves in that the particles vibrate parallel to the propagation.
Propagation is defined as the direction of energy travel in a wave.
When Mr. Peterson produces a longitudinal wave, the displacement of the compressions is parallel to the propagation.
Sound is a longitudinal wave, so the displacement of the particles is parallel to the propagation of the wave.
The velocity of sound is constant, in this case because the medium, which for sound is air, is not changing. The speed of a wave is determined by the medium it travels through. In this case, air is the medium, and since the temperature, pressure, and humidity remain constant, so does the speed of sound. We'll turn this speaker on and produce a low frequency wave.
As the frequency goes up, the speed stays the same, so therefore the wavelength gets shorter. Higher and higher frequencies have shorter wavelengths because the speed is constant. When you reduce the frequency, the wavelength must get longer because the speed stays the same.
The same is true for transverse waves. As long as the medium is not changed, the speed of the wave will stay the same, but the frequency and wavelength may change inversely with one another. So, how do we determine the speed of a wave? Well, we can measure the distance of the wavelength, which is measuring from crest to crest. And we can also get the period, the time it takes to complete one cycle. So the wavelength in this case is 6 meters. And since the period is 2 seconds, we can use the formula v equals d over t to calculate the speed. 6 meters is covered in 2 seconds, so the velocity is 3 meters per second. Box that puppy up, and we're done. So here's an interesting derivation. If we start with the formula v equals d over t, we know that the distance covered is a wavelength, and the time it takes to cover that distance is called the period. So now we have v equals lambda over t. Now, if we recall that t equals 1 over f, we can substitute in 1 over f for t, the period. That will give us v equals lambda over 1 over f. Multiplying through by f over f, we can cross them out, and we're left with v equals f lambda, the formula for the speed of a wave. This is so exciting. Let's double box it. Oh yeah.
Waves, which require a material medium for their propagation, are called mechanical waves. For the next part of this presentation, I will use the term waves to refer to mechanical waves. Waves are able to propagate through a medium because of the interaction forces between the particles of the medium. These particles could be atoms or molecules. To understand wave propagation, it is good to imagine the particles of the medium as connected by springs. The springs may represent the interaction forces between the particles of the medium. Let us first consider transverse waves. They are waves which make the particles of the medium vibrate perpendicular to the direction of the wave motion. How can transverse waves propagate through a medium? When your hand pulls up the first particle of the medium, the next particle also feels the upward pull of your hand through a spring linking the two particles. The same thing happens to the third particle. The particles of the medium do not move at the same time because of inertia. Inertia is the tendency of objects to resist change in motion. Because of inertia, the particles appear like giving a delayed reaction. It takes time before they could move when acted upon by a force. When the particles are heavier, they tend to have greater inertia. Waves move slower when the medium has greater mass. Similarly, if the first particle is pulled down, it also pulls down the particle next to it. The forces between the particles enable them to influence the motion of those next to them and, in effect, pass the disturbance that they experienced or felt to neighboring particles. The particles of the medium return to their undisturbed positions also because of these forces. But the energy used in creating the wave is carried up to the end of the medium. The particles of the medium are not carried along by the propagating waves. Now let us consider longitudinal waves. They are waves that make the particles of the medium vibrate parallel to the direction of wave motion. When you pull and push alternately one end of the medium, the first particle of the medium moves left and right from its original position. The push and pull on the first particle are also felt by the next particles through the spring linking them. Each particle then moves left and right in succession as the waves propagate. But then again, the particles of the medium are not carried along by the propagating waves. Do you know now why they do not move at the same time? Remember the magic word inertia.
Electromagnetic waves. Electromagnetic waves are waves that can travel through a vacuum. By vacuum, I mean space. Okay, outer space, vacuum, emptiness. They do not require a medium. The important thing to note is that they do not require a medium. They can travel through a vacuum. Here are a couple of examples. Visible light. We see this rainbow here. Rainbow, all the light you see here are caused, or the phenomena caused by electromagnetic waves. In addition, you have radio waves. And here's the actual full list. Here are all the different types of electromagnetic waves that have been discovered. Gamma rays, X-rays, UV rays, which you wear sunblock to protect yourself from, visible light, which you see here, infrared waves, microwaves, and finally radio waves.
To understand light, we need to understand a larger group of energy, known as electromagnetic waves. Light is a very small part of the electromagnetic spectrum, and all the types of waves in this spectrum share certain properties. All forms of electromagnetic energy, including light, are waves. And as waves, they all have frequency. Frequency is usually defined as the number of waves that pass a certain point in a second. The difference in frequency is a result of the size of the wave. A longer wavelength corresponds to a lower frequency. Electromagnetic waves are organized into types based on frequency. At one end of the spectrum are radio waves, which have the lowest frequency. The spectrum moves through microwaves, infrared rays, visible light, ultraviolet rays, and X-rays, to gamma rays, which have the highest frequency.